Our distinguished speakers and facilitators are pioneers in this field, ready to share their expertise and insights that will undoubtedly inspire and broaden our understanding. As we navigate the landscape of AI for music, let us unravel the mysteries of code and algorithms and appreciate the profound impact this fusion has on our artistic landscapes. That being said, I welcome you all to the first session of the program. This talk promises to unravel the intricacies of audio signal processing. I would like to invite Dr. Vipul Arora from IIT Kanpur. He received his BTech and PhD in electrical engineering from IIT Kanpur. During his postdoc at Oxford University, he developed speech recognition systems using linguistic principles with applications in automatic language, teacher, and speech recognition for low resource languages. At Amazon in Boston, he worked on audio classification for developing the Alexa home security system with research focusing on classification with imbalanced data. Please join me in warmly welcoming Dr. Vipul Arora.
We have Bengal music, I think by many others. We have Gurmat Sangeet or music of Punjab, starting from Guru Nanak Dev Ji. We have Assamese music by Shankar Dev. We have Mirabai, who is very popular in North India. She has her own music style and music traditions. We have Tukaram in Maharashtra. So India is a land of music, traditionally and historically. And presently, our society is full of music. There is music in every occasion of life. When somebody is born, there is music. This is a music from Bihar.
Yeah, so this is the birth music. Whenever somebody is born, people sing, people play music, and this is a tradition we have which I'm showing here. Then weddings. Then army. Even death. So in every aspect of Indian life, we have music, folk music, cultural music, traditional music, classical music. And of course, music has a role to play in cognition, health. Music has a role in education, in cognitive development of children. So that's why in schools, we have music education. So music is everywhere. Now, these days, we have technologies such as Alexa, Siri, Google Home, which deal with audio and which process the audio for various very impressive applications. We have AI for music or the audio in industry, industrial audio, for health, uh, for education, for environment sounds. We have all of you listen to YouTube. You have music recommendation systems, so you're all familiar with music recommendation and audio recommendation systems. Music composition, AI and technology can help in composing new music, and even in scientific research, like in neurolinguistics or linguistics or cognition. We have Professor Venu Alluri here who will be speaking more about this. So let's dive into some basics, like what is music? So it this is a piece of Indian music where we have a singer who is singing. We have Kanpur playing in the background, and we have tabla playing as well. But what is digital audio? So somebody sings, yes, we can hear, but then we can also digitize it. We can process it with our computers. How do we do that? We have our microphone, so microphone basically has a diaphragm which vibrates whenever the sound falls on it. When this diaphragm vibrates, it generates a mechanical motion, and this mechanical motion is converted into electrical signals with the help of electromagnetic induction, the dynamo. And then this signal, this electric signal, which is read out from here, it is read by our computer, and the computer can then save it and do the processing. But before this happens, there is an important step here. And the step is that the computer cannot store the continuously varying sound. It cannot store analog signals, in other words, because the reading of the dynamo is a continuous variation in voltage. So because our computer is a digital computer, it has to sample the audio and store those values. So it has to sample it along time. It has to sample it along amplitude. This is called sampling and quantization. So sampling means we have a time series, or we have continuously varying signal. We don't save all those infinite number of values. We save only discrete samples in time. So, and how fast should our sampling be? It depends on the frequency of the signal, or how fast the signal is varying. If signal is varying very fast, I have to sample it at least double that speed. If signal is slow, I can sample at a slower pace. And humans can generally hear in the range of 20 hertz to 20,000 hertz, although it's a very large range, but an average human hears in a range which is a subset of this range. Popularly, 44.1 kilohertz sampling rate is used for CD recordings. Likewise, when we sample in time, every value which I obtain maybe some historical connections. Yeah, I'm not sure, but some historical connections. Yeah, Professor Srinivas can answer finally.
The television requirement of fraction of that. So the standardization of the CD happened to be compatible with the television transmission its frequencies, etc. So it's a studio requirement that came in, not from our sampling. Also, stereo is part of it. Totally 1.44 megabits per second.
Yes. So generally we record. Generally, since we have 2 ears, and when we put headphones, it has 2 speakers. So generally, people record in stereo settings, which means there are two microphones which record both the channels, and then they correspond to our two ears. Yeah, so then the next part is quantization. Let's say I sample at some point, there I get a continuous value, which is, let's say 0.556677, and there is no end to the precision. It's a continuous number depending on the precision of my measuring device. But we quantize it, which means we stop at a particular point. We say that, okay, I only want this much precision. And that is called quantization. Generally, we decide how many bits I want to use to store that number. Let's say I decide I will use 16 bits. This means my precision is fixed now. And generally, this 16 bits is fixed. How is it decided? Because when we listen to audio, if let's say I use only single bit, then the audio quality will be very bad and I will not be able to understand it very well. But let's say somebody uses 100 bits. The audio quality is so good, but it doesn't matter to me because whether you use 100 bits or 101 bits, my ear cannot perceive that difference. So why waste our resources? That's why 16 bits is an acceptable number, which gives a decent quality. So that's what. So you have a signal like this, and in the time we have sampled, in the amplitude we have sampled. So this gives us something called a waveform. So when I record our through the microphone, but when the audio is recorded, it leads to a one-dimensional time series or one-dimensional signal, which the dimension is time and the y-axis is amplitude. And I save it, and that's what it looks like. So here we have saved tabla sound, tanpura sound, human sound separately, and we can mix all of them, which means we can simply add all of them in the simplest setting, and that leads to the mixture of audio. I have used a software called Audacity to plot this. It's a very simple software. You can install it on your computers. It's free of cost. Now we need to process the audio. For processing, we need some mathematical model for the audio. So here I'm just plotting the waveform of audio, or the human speaker or human singer. I have used a software called Prat to plot this. Let's zoom in and see how does the signal look like if we see it very closely. What do we see here? So audio is a continuous and periodic signal. It's a periodic signal. And what tool can we use for periodic signals, for analyzing periodic signals? Fourier transforms. Fourier transform is a very popular tool for analyzing periodic signals. So let's use it. So what is Fourier transform? Fourier transform means we take a dot product of our signal with a sinusoid. So in simplest terms, that's the Fourier transform. So xn is my signal, and this is a sinusoid written in the Euler notation, the complex form. And that's the Fourier transform. So what does Fourier transform do? So let's say if my x of n or my signal is sinusoid, I multiply it with the sinusoid, I will either get a very large value or zero, right? I will either, so if my my sinusoid and the signal have same frequency, when you take a dot product, you get a very large value. As you can see here, this peak and this peak. So this sinusoid frequency matches my signal frequency. So I get a high peak here, which means the dot product is very large. But if my sinusoid frequency is something different, then, okay, some trigonometry. What is sine A into sine B? It's another sinusoid, right? Some sine A plus B by 2, sine A minus B by 2 plus cos something. I don't remember exactly. So it's another sinusoidal signal. And if you integrate the sinusoidal signal, what do you get? 0. So that's what happens in the other frequencies. So that's why we get 0 here. But when they exactly match, then it becomes cos 0, which is 1. So that's why you get a large value here. What is the advantage? There is another advantage of Fourier transform. The advantage is that even if we have mixed sinusoids in my signal, my signal is periodic, but it is a mixture of multiple sinusoids. Then when I multiply it with individual sinusoids, I can identify what all sinusoids are present in my mixture. My mixture of sinusoids can be decoupled, or it can be again decomposed into original sinusoids, right? So let's say here in this signal, I have this sinusoidal frequency and this sinusoidal frequency present. That's what I get from Fourier transform. So that's the advantage of Fourier transform. If you want to read more about Fourier transform, then you have second-year book called Signals and Systems, which I'm sure you might have, you might be still remembering. If I say something, let's say I can see here a frequency of 122 hertz. It's a higher pitch. And it's 142 hertz. You can see the peaks are in this way. And the first peak appears at 142 hertz. Still higher pitch. I get the first peak at 163 hertz. So what I find here, in real audio, when I sing or when I say a constant frequency, I have that particular frequency, but also there are other peaks, which means there are multiples of that same frequency. So which means here it's 122, then 244 hertz, then 366 hertz. So the integer multiples are there where my peaks are appearing. This is a very important concept to understand. Is it clear? Any questions? Please feel free to raise hand. Sure.
I always give feedback from the reviewers when I write papers. That there is a distinction between the pitch and the fundamental frequency. So, and they always ask me to be very cautious about this thing. And second thing they write that the pitch can also have non-periodicity, meaning it can be heard and perceived. So, like from this, of course, I am saying that what you are talking is a measured pitch. So what do you say? Like, and they say that, you know, when we say about a measured pitch, we should write F naught as a fundamental frequency.
Yes.
That is one. Yes. And secondly, when I'm speaking normal speech and then singing and then humming and then audio, so the pitch, the terminology of the pitch, I think is different or same?
Okay. Yeah. Thank you very much.
And I'm just very frank to what I'm getting the problems from the reviewer.
Sure. Yeah. Thank you. I agree with you. Thank you very much. Yeah, pitch is a perceptual quality. Pitch is a perceptual property. When I hear a sound, it has a pitch which I can hear. And when I say, it has something higher. Some aspect of this sound is different from that sound. Although I'm saying the same vowel, but some aspect is different. What is that aspect? That is the pitch. Now, to mathematically quantify that, what is the difference and how we mathematically quantify it? So we look at the periodicity of the signal. We find, oh, this is periodic, but this has a fundamental frequency or a kind of a time period which is different from this the periodicity of the other signal. We call that as F naught, or the fundamental frequency. And it is seen to correlate with what I hear. My perceptual pitch and this signal periodicity, they tend to correlate. They correlate very well in most of the cases. That's why we call pitch and F naught mostly are same thing in many of the cases. But of course, we have to be careful that in many cases, they may not be same also. There are examples where I hear some pitch, but then I don't see that in the waveform. That periodicity does not appear in the waveform as rightly pointed out. Thank you very much. And one example is like when you have hand cymbals, when you chime them together, you hear a pitch, but then when you look at the signal, it looks very non-periodic. Other example, which one of our experts here in IIT Kanpur has worked a lot, is Tanpura. In Tanpura also, seeing the periodicity in the signal and what you hear, the pitch, they don't correlate very well. Yeah, thank you very much, sir, for raising this point. Yeah, but in simple terms, like to keep things simple, you can, in ordinary cases, generally pitch and F naught have this kind of relationship. That when the F naught is higher, pitch is also higher. Okay. Now, when I say and e and what is the difference? Where is the difference? It's certainly not in the pitch. I can say e at the same pitch, but what is different then? So to see that, again, we go back to the spectrogram or the spectrum of this periodic signal. So what we find is when I say the spectrum looks like this. When I say E, spectrum looks like this. So what has changed? The peaks are still there at the same frequency levels, but what has changed is the overall envelope of the spectra. This is the magnitude spectra, the Fourier transform. The envelope has changed. As you can see here, there is some high energy here, then some high energy here, but here you have high energy and here very high energy, and then here some other high energy regions are there. So this spectral envelope tells you about what are you saying. Are you saying or E, or likewise And if you go to non-periodic sounds like S and F, so what do you find here? They don't have peaks like that because it's not a periodic sound. They don't have peaks, but what you get is kind of, people call it as white noise or some noisy kind of signal, but still it has a spectral envelope and they are distinct. For example, the spectral envelope of S sound, you have high frequency components have large energy, whereas in F sound, you have low frequency components have high energy, then middle frequencies have low energy. In this way, so you can still distinguish between S and F by looking at the spectral envelopes. So which means spectral envelope is a very good quantifier, you can say, of different phonemes. And same thing happens with instruments as well. If I play flute, if I play harmonium, if I play sitar, if I play clarinet, so they have different signatures or they different spectral envelopes. So that's how I can distinguish between different instruments. So using this understanding, the two things which we have read, number one is when I change my pitch, my fundamental frequency changes or the position of peaks in the spectra, they shift. When I say a different vowel or I use a different instrument, then the spectral envelope changes. So using these two observations, we can come to the filter theory. So what is the filter theory? You have read it in the signal and systems courses. So there is something input, some input signal, there is some filter, and there is some output signal. So how we model our speech, I say something, then my lungs produce some signal, that is the input signal. It has a, let's say, fundamental frequency when it crosses our epiglottis. And then if I change the shape of my mouth, I can say, E, O. I'm just changing the shape of my mouth. Rest everything up till here is same. So I can model this as a filter. So this is my input signal, which is reaching up till here. And then I change the shape of my mouth and it gives rise to different sounds, different vowels, let's say. So this can be mathematically modeled as a linear time invariant filter, which means my input signal xn, it passes through a linear time invariant filter h of n, and output is the signal y of n. And this operation is called convolution operation, which means my y of n is related to x and h in this way. And when you go to the Fourier transform domain, there my spectra, let's say the spectrum of this is y of k, spectrum of my input is x of k, and spectrum, or you can say the spectral property of my filter, LTI filter, or spectrum of my impulse response is h of k. So I can simply multiply them. If my xk multiplies with hk, I get the spectrum of yk, spectrum of output. That's a very useful result because now I can visualize everything as just multiplications happening. So that's what we do to come up with something called a source filter model. What happens in a source filter model? We assume the same LTI filter concept. So my input, it just has peaks. Just peaks at the particular fundamental frequency. Let's say when I say it has peaks at a particular at integer multiples of a particular f naught. And then it passes through my articulator, which I modeled with another spectral envelope, you can say. And when they multiply, I get my final output spectrum, which is having peaks plus the spectral envelope. That's the source filter model in a simplified way. And as I change my filter with spectral envelope, I produce different vowels. If you want to read more about it, there is a book called Discrete Time Speech Signal Processing by Quartieri. I encourage you to read this book, which has further details. Okay, this is the theory of digital signal processing. But how do we make real applications, real audio applications with this theory? Okay, I just want to pause here for a moment. Do you have any questions? How many of you are hearing this for the first time? Just raise your hand. Okay, 1, 2, 3, 4, 5, 6, 5. Do you have any questions? No? Okay. If you have still questions, you can ask me outside also. But if you have any questions which stop you from understanding further, then please do ask now. Okay. Now we are going to discuss about real applications with this knowledge. Let's say if I ask you, can you make a system which can identify what pitch I am singing? When I say, what is this pitch? I say, what is this pitch? Can you make a computer program to do this? Yes? How will you do it? Take Fourier transform, look at the peaks. The first peak gives you the fundamental frequency that corresponds to the pitch, right? If I ask you, tell me what vowel I'm speaking, how will you do that? Take the Fourier transform, look at the spectral envelope, and from there you can tell whether it's a or e or u, right? So that's what we are going to discuss now. How do we design those representations? Now, when I say representations, it means it has to be compact, minimal in size, because Fourier transform is a large quantity. Like let's say 1024 point Fourier transform will have at least 512 values of magnitude spectrogram. So such a big representation, but I want to compress it to save my computations later or to do my decision making quickly. I want to compress it to a smaller space. So this is called representation design. That representation should be very small in size. The other quality it should have is this representation should be distinguishing for what I am interested in. For example, if I want to identify what vowel it is, then it should be independent, or it should really distinguish between a and e, right? For example, if I tell you the pitch, can you tell me what vowel it is? If I tell you the F0 is 55 hertz, can you tell me what vowel it is? So that's not a good feature for this task. So my feature should be distinguishing for what I am interested in. And likewise, it should be invariant to what I am not interested in. Let's say if I want to know the pitch or the fundamental frequency, I'm not interested in the spectral envelope. So I don't need the entire spectrum or the spectral envelope. If simply somebody tells me what is the frequency of the first peak, that is sufficient. So this is called representation design. Another quality which our representation should have is that they should have uniform sensitivity in the space. We will discuss more about this property in the hands-on session by Anoop. But for now, I will just give you some examples of what do I mean by this uniform sensitivity. Okay, this we have discussed. Okay, let's look at this sound. Simple sound, but if you look at its Fourier transform, the magnitude Fourier transform, it looks like this. It's very difficult to distinguish, to find out the spectral envelope. Why? Because these frequencies, they have so little power. So what we do is we convert them into log frame. So what happens when we convert the amplitude into log frame, into log? frame, what I get is even the low frequencies and the high frequencies, they become comparable now, right? Because when you take a log, what happens? The differences in the means it compresses the dynamic range in technical terms. It compresses the dynamic range of my signal, which means if I have something, let's say the value 20 will appear log 20. What is log 20? It's almost like log 2 plus 1, so 1.3 something. And if you have something like 0.2, how much will the log be? It's -1 plus log 2. So it's almost like -1 plus 0.3, which is how much? Minus 0.7. So you can see now in a very small space, you have 1.3 and 0.7, which are very much comparable now in your space. And that's what you can see here, that your spectral envelope becomes much more enhanced and the differences become much more enhanced. That's what I meant when I said the sensitivity should be uniformly spread in the space, that you can see it very clearly. So generally, we express our amplitudes in a dB scale, which means 20 times log to the base 10 of the amplitude. So this logarithmic transformation helps us to enhance the differences. Likewise, in frequency, we know that our sensitivity to frequency, it changes with frequency. Let's say there are two frequencies. Let's say there is a frequency of 100 hertz. Now, if I add 10 to it, 110 hertz, they are very, very distinguishing, means that I can perceive them very, very clearly. But now if you take a frequency of 1000 hertz and add 10 to it, 1010 hertz, our ears can hardly distinguish between these two frequencies, which means our sensitivity changes with frequency. If at very high frequencies, my sensitivity is less. Or in other words, more mathematically, our sensitivity is in terms of multiples of frequency. If my 100 hertz, it becomes double. So how much change I perceive here versus if I have 1000 hertz and it becomes double, how much change I perceive there. So that's why what people generally use is not the frequency value, but the log of the frequency. That helps us to, again, make our space uniformly sensitive, which means the differences are properly represented in a compressed space. And you can see how do we achieve it in the spectrum. In the spectrum, we use something called a Mel-spaced spectrum or Mel spectrum or a logarithmic spectrum, which helps us to understand these differences or compress these differences and enhance these differences. So this is a filter bank. You multiply the filter bank with these energy values and you get the numbers out. So that's how we do it. I don't want to go into the mathematical details, but that's what the idea is, that we want to get representations which are very compressed and which are kind of uniformly sensitive to differences which we want to, which we are interested in. Then we have to get a spectral envelope. Now, let's say if I want to extract the spectral envelope of this audio, what do I do? First of all, okay, I am plotting here the spectrogram where the amplitude is in logarithmic scale, frequency can be in logarithmic scale, although in this figure it is not. And then I want to get the spectral envelope. So what do I do? Now, if you see this figure, if I ask you to get the spectral envelope, one simple thing you could do is, okay, pass it through a low-pass filter. If you pass it through the low-pass filter will pick up the overall variations, the spectral envelope kind of variations, and it will not worry about the exact peaks or the high frequency variations, right? That's what the meaning of a low-pass filter is. So we want to now pass this as a signal to a low-pass filter, in simple words. That's what is the concept of Mel frequency substral coefficients. So basically you take a Fourier transform of this signal and take the low frequency components which capture the overall shape of the spectral envelope. And that is sufficient to represent what vowel it is, right? This is called MFCC features, and generally about 10 to 15 MFCC coefficients are sufficient to capture the distinction between different vowels or different instruments. Okay, so now you are ready to make Alexa. Now you are ready to make AI systems. And so this is all is the fundamental DSP which you need to make these systems. Any questions?
In MFCC, we have the filter band. So each of those triangles get multiplied with the whole spectrum and we get one value. And so the number of features will be the number of filter banks.
Yes. So number of filter banks there, let's say you used, okay, I'll go back to the, so these are the filter banks. Let's say this blue one is my one filter bank. I multiply this with the spectrum, I get one value, dot product, so one value. Then I multiply this red one with the spectrum, I get another value. I multiply this green one with the spectrum, I get another value. In this way, I get 20 or 40, whatever is the number of filter banks, that many values. That is my one vector. And then I take the DCT of this, the discrete cosine transform or the Fourier transform of this, and take the low frequency components.
So is there any some thresholding operation going on to take the low frequency components, or
thresholding?
The DCT?
Thresholding means because I'm picking up the low frequency components only, let's say from frequency, the minimum to the first 10 coefficients, let's say. That's it.
Oh, just multiplying it with cosine
DCT.
cosines and then.
Yes. So like you got a spectrum, and in the spectrum, you take the low frequency part, and how big part you want to take, that is in your hands.
Thank you.
Thank you.
It is not enough to use 20 filters here. It doesn't mean that you have 20 coefficients. You can use 20, 30 filters, but you can get 13 coefficients because of the in the DCT implementation. When you set how many coefficients you want, basically, that becomes your MFCC feature output. That's a 13-dimension static feature. Even though you have 20 or 30 filters used in MFCC computation, in my understanding. So DCT has the role to play, in the designing the dimension of each vector.
Yes, yes. Capstrom. Yeah, you can study Capstrom. I refer to the book called Quartieri. It has further details. Capstrom is basically you take the spectrum, like this is spectrum, and again take a DFT of this or DCT of this. So that becomes Capstrom.
Those that you are writing this, I actually call it Q-Friends.
Q-Friends. Yes. Yes.
Yeah, I had a question.
Yeah. Yes, please.
I wanted to understand the distinction between the spectral envelope and the signal. So spectral envelope is modulating the amplitude of the signal. That's the base signal, right?
We are discussing in the spectral domain, not in the time domain, in the spectral domain. So let's say this is my spectrum, then this is the envelope.
Yes, so the envelope would also have its own frequency, right? If we
envelope, okay. So generally a frequency means one peak, right? In the spectrum, you see one peak that is like in time domain, that is one frequency.
Yeah, I'm wondering about if the envelope also has a comparable frequency that is comparable with the signal itself. Then how can one distinguish between?
Generally, the spectrum you can see here, it is not having one peak. It is like a spectral envelope is like the spread over the entire spectrum. It's like a spread over the entire spectrum. I mean to say that if it also has a very particular peak, then it will filter out all the frequencies which are outside, only take that frequency if it is present. For example, if you have, technically it's called a notch filter, okay, if you know the terms, but it means that if my input signal has a various frequencies present and my filter has got very sharp peak at only one frequency, then my YN or my output signal will have only that frequency present if it is present in the input signal. Basically, xn or x of omega and y of and h of omega, they get multiplied. Then if x has a high value at that frequency, h has a high value at that frequency, then output something is there. Okay. But if x has no power in that frequency, then y will be just a flat signal. Okay, look up notch filter, you will understand more about it, and we can discuss offline. Yeah. Yes. Small board. Yeah. Sure. Parampreet, maybe something to write on, if possible, from next sessions you can arrange. Thank you, sir. Okay, so we are now ready. Are you confident enough that you can make Alexa? Ajay is here. Okay, not yet. So there are some things which are still, they need attention. So when I speak something, it's not just one thing I'm saying. I'm not saying all the time. There's a dynamic behavior involved, which means I say apple, I say father, I say things change. So I need something called time series analysis. And how do I do it? That's also very simple. My signal or my audio signal is not constant with time. No problem. Take small windows and assume that within these windows, things are almost constant. When I say father, there is some window where this comes. So there my will be constant. So basically, within these windows, I can assume stationarity of my signal, or the characteristics don't change much. And I can do spectral analysis within these small windows. And then put these windows together, means all these spectra together, and it gives me a representation called a spectrogram. So this is my time varying signal, time series signal, the time domain signal. If I take small windows, plot the spectra and put them together, like one next to other, like this is the first window. I have plotted the spectrum now in a vertical direction. So, and the color represents the amplitude. So you can see high frequency here at this frequency. So y-axis is the frequency now, x-axis is the time. My first window, second window, third window in this way. And you can see here, this frequency is prominent, a bit higher frequency, a very high frequency, right? This is called a spectrogram. Just spectra of small windows put together in a kind of space. Now, if you look at audio. So you can see here sa, then re has a higher frequency. The first pitch, the first peak has moved up. Then ga, further it has moved up. Then again sa, again re, then it has come down. So you can see in the spectrum, in the spectrogram, you can see what the person is saying or singing. And in fact, there are people who can look at the spectrogram and can tell you what the person is saying or singing. And there is an entire book on this. It's called Acoustic Phonetics, this big book. And it discusses in detail how to read spectrograms. And the people they can become expert spectrogram readers. They don't need to listen to you. They just look at your spectrograms and they can tell you what you are saying. So it is possible. But only in ideal situations. Only in ideal situations. I have to really articulate very slowly. And yes, you can make you can make rules also to make your computer recognize what they are saying. But there are problems like this. Audio, please. So what do we see here? There is context, which means if I say before that has come and then the has come, so father, then my changes a bit because of that context. There is running speech. When I speak fast, then I don't touch everything properly. As you can see here in these notes, you don't see any flat notes there. Although you are hearing those frequencies or those notes in the music, but the singer is not stopping at any note, and it's continuously running and jumping, and it's very difficult to tell from the spectrogram what note it is. Then there are variations because of speakers. When I say versus you say there are differences, right? And we can hear it, but how do we see it in the spectrogram? It requires it's much more nuanced analysis, which is very difficult. When instruments change, spectrograms change. My flute may not look the same as your flute, or the spectrograms won't look exactly the same. Languages change. When I say father, I am a person from Hindi background versus, let's say, Zihao, who has a Chinese background. When he says father, his and my will be different. Then recording equipment may change. This microphone and your mobile microphone, what they record, there will be differences. Acoustic conditions change. What you record here in this auditorium versus what you record out there in hostel mess. They have a very different appearances. How do we deal with all these variations? That's why machine learning can be helpful here. So what is machine learning? So in machine learning, you have a parametric model that learns these feature transformations. So this is the model f theta. It learns, let's say, I want to make an application speech to text. I want to tell what are you saying. So instead of making rules that, okay, if the spectrum is like this, the spectral envelope is like this, then it is a. Instead of doing that, I can make a computer model which will say, okay, you multiply your x with some f of theta or pass it through some f of theta, and y hat is the output of the model. It will say whether it is a or e or u, etc., etc. Right? And this f theta, it is trainable, which means it's a parametric function, maybe like a straight line. Like just like you have a straight line, how many parameters does it have? 2 parameters, the slope and the intercept, y equal to mx plus c. So m and c are the 2 parameters. So similarly, f theta is also a parametric model, maybe not single straight line, but multiple straight lines and some other non-linearities. So, but that's what f of theta is. And it places itself, these lines, they orient themselves in such a way so that your x can map to the desired y hat, which could be phoneme, which could be frequency or the pitch, which could be what instrument it is, which could be what speaker it is, etc., etc. So you can learn such mappings from for applications such as speech to text conversion, audio to audio transformation, let's say speech enhancement or speech transformations. You want to change this one speaker into another speaker. You speak something and you want to make it sound like a baby speaking or a old person speaking or a person from a different language speaking. All these are possible if you modify this f theta accordingly. Audio to labels or classes, you want to classify whether it is this instrument or that instrument. Audio to recommendations, you want to recommend music, etc., etc. So these things are possible. But how do you design this f theta? How do you kind of train this f theta, or how do you set these theta parameters in such a way that the model does what you want to do it, what you want it to do? That is called something called training. So in training, what we do is we have the model output y hat, and we have the desired model output y. Let's say I want, this is an a. So you have to tell, okay, if I have this x, this y should be a. But y hat in the beginning, if it is random, it may say anything. It may say, oh, it's a, e, u, anything. But you want to make sure that it says it's an a sound. And how do you do it? By modifying the theta. You modify your theta so that your f theta gives the right output. That is all about machine learning. This process is called optimization or training. And now what do you need for this? You need a book, PRML. This is a very nice book on basics of machine learning, which you can read. But what you need here is this labeled data. which means you need pairs of X and Y. Or if this is the sound then this is the label This is the sound E, the label is E. So this labeled data you need, and this is called supervised machine learning. And what are the different methods available? What are the different kinds of parametric models or non-parametric models available? So you have Gaussian mixture models. They were very, very popular. Still, they are popular, but they were very popular for speech recognition some time ago. Then you have hidden Markov models, which model not just static windows, but dynamically evolving things. When I speak, things are dynamically evolving. So hidden Markov models help me to model that dynamic evolution as well. Then we have multi-layer perceptrons or neural networks. We have support vector machines. We have convolutional neural networks, recurrent neural networks, and so many other variations like transformers, and the list is unending and it's still growing. But the major bottleneck here becomes annotated data. So you have to have these sounds like E, etc. And somebody has to sit and label these. Okay, this is an sound. Listen to it. Like you have put a headphone, listen to the sound, and write down, this is an sound. This is an E sound. This is an apple. This is the father. This is the sentence, I am eating an apple, etc., etc. That becomes very labor intensive. Why do we need the data? To train our models. But then before that, all this effort has to be done, which is labor intensive. So recently, or some time ago, a new method came up where we design these features with the help of self-supervised learning. So what is self-supervised learning? You still have the model, you have the X, you have Y hat, but I don't have Y. I don't have to manually create the Y, the desired output. I don't create it manually. Rather, I use something intelligent. What is an intelligent thing? I take this original spectrogram. I have the original speech. Just take that speech spectrogram and remove some portion from it and treat it as your target. So the task becomes, given this spectrogram with some hole here, I want to fill up this hole. So my Y hat should fill up this hole. And how do you do that? You use the model to do it. And the target is already known to you. You have only created the hole. You know what was there in the hole. So this is called self-supervised learning. So basically, you modify your data in such a way that you get both the input as well as the target from the data itself. And what is the end result? After this whole exercise, you have trained your model, throw away the final layers of the model or some part of the model, the final part, throw it away. And this other part, that becomes a very good feature representation for you. It becomes a very good extractor of features. And if you keep it small enough, you can control how big features you want in the output. Means you can control the size of your features. That's called the self-supervised learning. And in these sessions in the WiSSAP, you will hear these concepts in many, many times, but these are the basics. And whenever you get confused, you can go back to these basics and kind of give yourself confidence that it's nothing new or it's nothing very difficult to understand. Thank you very much. We still have some time for questions.
Hi, thanks for the talk. Was self-supervised learning also part of the Bishop? Like, can Bishop be a good resource for that?
I see self-supervised learning as a tactic which has become very famous. So the basic concepts are still the same, which are there in Bishop's book. It's just a kind of tactic to make the data available for training.
And these, like when we are using these as the representations, like, of course, I'm assuming explainability suffers a lot.
Yeah, good question. So the point here is that earlier you knew when you took Fourier transform or something, you knew your output corresponds to what. For example, you look at the output of Fourier transform, which is spectrum. You know the peaks correspond to the fundamental frequency, the spectral envelope corresponds to what the quality of sound or what the phoneme it is. But what do these outputs correspond to? We don't know. So it's because it's all happening by a very complicated set of transformations or nonlinear and linear transformations. So it becomes difficult to interpret what does each output correspond to. So that becomes a new area of research called explainable AI research. Yes. I don't know if there are talks around that part, but Ziha will be doing that.
Instead of STFT, has wavelet or other transforms been more effective for this type of work? I mean, what is the literature telling us? Instead of STFT, is there any other input that is good for such analysis?
Yes, thank you very much for a very nice question. So Fourier transform or STFT is not the only method, although this talk focused more on Fourier transforms, but they are not the only method. There are other kind of transforms also available. For example, Sir mentioned about wavelet transforms. So instead of multiplying with sinusoids, you can multiply with some other signals also, right? So that's what becomes wavelet transform, which is more general than Fourier transforms. So there have been some works in those directions and multiple other directions. Some people say, why use Fourier transforms at all? Just feed your raw waveform into the input and try to get something in the output. So all those research works are being carried out, and certainly they are also there, which I didn't cover in the talk. Thank you. But these are the most popular ones, so I just picked this up. Wave-to-Wave 2.0 uses, does it use spectra or not? I don't remember. Maybe somebody who works in Wave-to-Wave 2.0. Adiraj is there. It uses raw audio, right, as input. Akanksha, yeah. Yeah, it uses raw audio as input, does not use spectra.
Sir? So in this self-supervised learning example, so we would be learning on one example itself. So won't it be biased towards that example?
Good question. Yeah. So this is just one representation, the one representative example. But now you have, let's say, thousands of audio files available. You can create such XY pairs from all those files, no?
But we are just trying to reduce that number, right?
Reduce the
number of examples.
No. They are unlabeled data. We are trying to reduce manual effort.
Okay.
How much manual effort was needed to pick that data? So very little as compared to manually listening and writing down what did you hear.
Yeah,
thank you.
Okay. For security analysis.
Your question is?
Are the same features at like WebCC? Or how for the sentiment analysis, for the emotion, what features will it take?
Good. I discussed the principle of feature design. Our features, they should be compact. They should be distinguishing for what we are looking for. They should be invariant to what we are not interested in. Let's say when you want to do sentiment analysis, then what features will be useful there? I don't work in sentiment analysis, so I may not know. But those who work, they can tell you better that how do you design the features for that. So, but of course, using machine learning, you can also try extracting those features statistically. But of course, pitch and spectral envelopes, etc. All these features are useful.
Nice summary. I joined in the middle, so maybe you have covered this, but so as you explained, like the note explained the fundamental frequency of the sound, right? So, for example, 440 hertz has some meaning in that. It's a particular note. And wherever a baby is singing that note or somebody else singing or some different accents singing, they all will have that particular feature in that. Which, we can understand. So similarly, how does that say sayings just like the pianins what is the explanation for that? If you could explain it.
Yeah, you mean the sir sound?
Yeah.
Sir sound, if you look at the waveform, it is not periodic.
Yeah.
It is an aperiodic. So I will just go back to that slide. Yeah. So, and when you, it's aperiodic sound, not periodic sound. And when you plot the spectrogram, or sorry, spectrum of that sound, you don't see distinct peaks there. The peaks are not there. The harmonic peaks are not there. But still you see spectral envelope. That spectral envelope contains the information which can be used to distinguish sir from other sounds. Yeah.
Consistent around anybody's speak.
Yes, generally, sir is the easiest vowel to recognize. That's why Alexa has a sir. This I heard when I was working at Amazon. Thank you. That's it. Thank you very much. Then now we have coffee time.